All right, good morning, everybody. Hopefully you had a restful weekend. Maybe next weekend will be a little bit more restful with the 4th of July coming up. All right, so for tomorrow, we're going to finish chapter 17, part C, and that will just be a wrap up of pericyclic reactions. And then we have homework week 2 available that is due next Monday. And then your labs for the ethers and epoxide lab 3, that one we've already covered the content, so you could start with that one if you wanted to. And then lab 4 is reactions of dienes. Anytime in the lab procedure, if there's nothing listed in the tables with masses, then you don't have to worry about doing a procedure for that with how you did things. So for those parts, you don't have to worry about that. I think there might be one of those in the diene lab where you don't have to worry about a procedure, but just be aware of that for the future. If there's nothing in the table that gives you masses and asks you for yields, then you don't have to worry about a procedure for that. And I try to point that out also in the procedure itself where it asks for things in the notebook. Another thing I noticed on some of the reactions, some of you still have starting materials left. So if you're running your reaction, you can control how long the reaction takes, and you want to run the reaction to completion where there's no more benzaldehyde. If you started with benzaldehyde, there should not be any benzaldehyde when you complete the reaction. So just make sure you're aware of that. So some reactions will take longer than others. Some are quick. And if you have other things that are there, I know in the last lab that had the part C with benzoic acid where you were doing the Jones oxidation with sodium dichromate, some of you ended up with sodium benzoate for your product instead of benzoic acid. And that was something in how you worked up the reaction. Some of the workups, depending, I don't remember if it's water or acid, if you did the wrong workup, you ended up with the benzoate instead of the benzoic acid. So just be aware of that as well. And if pyridine is left in your reaction, pyridine is a mild base, so you would break that up with acid instead of water, and that should get rid of the pyridine. All right, and then we have an exam coming up Thursday/Friday, just before the holiday weekend, so you guys can enjoy fireworks. I don't know who's going to fireworks, but there is that. Questions on labs or homework or exam coming up? Okay, and this, the Diels-Alder joke here is probably lost on everybody just because it's very niche. But the URGF, I think it stands for girlfriend, but this would be the OH is an electron donating group, which is good. But then on the U part, there's just the diene file, which does not have any electron withdrawing groups on it. And then the other guy that she's not worried about, tells you not to worry about, has all these electron withdrawing groups, and that's why that's supposed to be funny. But again, not too many people will get that one. All right. So these are the answers to the quiz. I think just about everybody got number 1 for the nomenclature, so that was good. And then there's other products for substitution with PBr3 will give you Br in the opposite direction. If you react a Grignard with the ester, that's going to add 2 groups. So we're adding this one and this one. And you should end up with the alcohol. So these are the 2 groups that added here. And then for the epoxide, we're adding to the less substituted carbon. So we want something nucleophilic. So we use sodium thiol or NaSH there. That will attack here and open up the ring. The SH should attack on the back side of the epoxide, and then the water's there to protonate. Any questions on that first page? All right, for D there, we have excess lithium aluminum hydride. We're doing a reduction in this one, so you can look at your reduction reagents. The only one we have right now that can reduce carboxylic acids is lithium aluminum hydride, followed by water to get that alcohol. And then for the Jones oxidation, that's going to oxidize. Anywhere there's a hydrogen on the oxygen, we have 2 there, so that's going to go all the way to the carboxylic acid, and there's no hydrogens here, so that did not get oxidized, which I think most of you got. For F, we're looking at doing an oxidation to the aldehyde, so you could use PCC there, the DMP, which is the Dess-Martin-Pyridine, or you could use the Swern reagent, which was that COCl2 with DMSO. And then there's 2 different synthesis ones that you could have chosen from. So those are the answers for that one. Questions on any of the synthesis problems? All right, so I thought what we do is I'm going to look at some of these synthesis answers. And so this will just kind of give you an idea of some common mistakes that students made. And this is not to single anybody out, which is why I didn't put names or anything like that on here. But just so we can see how we can correct these mistakes. And so we don't get the same things in the future here. So the first line there is a synthesis with HX and XS with peroxide. And this was the product that was drawn here. And it could have been that there was groups left off. But in what I can see transformation-wise here is that we're adding carbons. Quite a few of them actually, which this reaction does not do. So if you were actually going to do this with those same reagents, and you should specify what X is. And usually the ROOR in our class for that one is fine to use that for the peroxide. But if you were going to add excess HX with peroxide, what that will do is add 2 X's to the end. So that would be what you would get for that reaction. And so I don't know, maybe the student was trying to get to this perhaps, but that would not be the best way to do that. So these syntheses are not working. This product would not be formed. And then there was a blank in this spot here to get to that alkene. So to get to the alkene, what we want to use is, that's going to be a couple of steps there. First, you want to add the carbon. And then we would just add CH3 because we're looking to add 1 carbon with a Br. And in that case, you need to specify what your R group is. Sometimes I've seen students write RBr. You want to specify that that's CH3Br. And then we're trying to do that, make that elimination, or I'm sorry, the reduction to the cis. So then we can use H2 and Lindlar's. So that will get us to the alkene. And this is one way of doing the epoxide with the OH and the Br. And in order to get that OH and Br, you can add Br2 and water. So this was a good intermediate to use the hydroxy and the bromine. And then to get to the epoxide from here, you just need sodium hydride or sodium hydroxide even. That will make the OH into an O-, which can then attack the Br. So that's how we could fix that synthesis. Does anybody have questions there? All right, on the second one, there's a couple of things here. The Br is fine. The Mg with the ethyl group, I think the mentality was to make this into a Grignard. A Grignard reagent is magnesium with Br. But this particular student wanted to add the Mg with the Br to get the OH, and then just add, this looks like propane to get to this product here. Maybe that was just ethane that was added to get to this product here. But the problem that we have is that Mg next to carbon does not exist. This doesn't exist. And then one quick way to get to the hydroxide, a couple of you did a couple of different ways. Some of you made it into the alkene and then use mercury to do that, which works as well. You can also just use sodium hydroxide to get to that step there. This would just be an SN2 reaction where OH is acting as the nucleophile. So that can do a swap out there. And then ethane by itself, this is not a nucleophile or electrophile. So if you just had CH3, that's very non-reactive, so that would not happen there. And then if you were trying to do a Grignard to form this product here, you would need a carbonyl. So we'd have to go through an oxidation step here before you could use the Grignard. And the Grignard is always going to be the R group, which in our case, we want to add 2 carbons and then the MgBr. And for the oxidizing reagent, you can use PCC, DMP, or the Jones reagent, or KMNO4. So any of those ones works. Right, questions there? Okay, in this first reaction here, we have Br going to alcohol. This one would be okay. This would be trying to do an SN1 reaction there. It would be slow though because this is secondary, but that one would work eventually. So you could do a swap out with water there. And then the student tried to use HBr in order to add the Br here. What that would do instead is just give you the Br back. So we don't want to do that. And then this is the correct-ish Grignard, but we need to have a carbonyl to do that. So there are parts of the synthesis that are okay, and then some things need help there. So for a Grignard, you have to have a good electrophile. All right, and then this, I think this is the last one I have. We have an alkyne with sodium hydroxide to try to form the acetylide there. But sodium hydroxide is not strong enough for that first step. You need to use the NaNH2. And then another problem that I see here, other than these are switched around, this is a nucleophile, and the Grignard is also a nucleophile. So we can't attack a nucleophile with another nucleophile. These would just be competing. So you want to make sure if you're having an acetylide, we need to make it electrophilic by adding CH3Br. And then that step will give you the alkyne with the extra carbon before you go to this step. And then this would give you the trans. If you wanted the trans, you would use the sodium with liquid ammonia. And then for the MCPBA, you would get the epoxide, but that would give you the other epoxide. You would get that one. So you want to use the E to get the epoxide. And that one is H2 Lindlar. All right, any questions there before I jump into chapter 17? All right, so for chapter 17, we started looking at dienes, and dienes can be cumulated where they're right next to each other. And notice that we draw a dot in the middle there so we know there's a double bond. Otherwise, it would just kind of look like this. And we don't know if somebody's drawing an extra long double bond or not. So you want to make sure you put a dot in the middle to signify that carbon there. You can have a conjugated diene, which means that there's double bond here, single, and then double. But if you look at the orbitals, these are all sp2. There's just that single one in between there. And then you can have an isolated double bond, which is one where there's a whole sp3 carbon in between. So you can have one sp3 in between or multiple, but there's going to be at least one there. You can also have conjugation with a heteroatom. So if you have this here, there's a double bond, single bond, double bond with the oxygen. This is considered conjugated. Or you have pyridine, which looks like benzene, but there's a nitrogen in the ring, and that is also conjugated with that heteroatom. Dienes can rotate along this double bond here. This would be an S cis double bond, and this one is an S trans double bond. So cis is, if you're looking at this axis here, these alkenes are on the same side of each other. And then for the trans, one is on this side and one is on the opposite side there. All right, questions there? All right, we have our first poll of the day. Which of these dienes is conjugated? Conjugated means that you have a double bond, single bond, double bond, with that single bond in between there. So the one that is conjugated here might not be super obvious because it's not in a ring, but it's external to each other. So here we have double bond, single, double. So this one is the conjugated one. If you have two double bonds right immediately next to each other, this is cumulated. And if you have sp3s in between, these are isolated. Questions there? All right, so 17A, we continue. The HOMO of a molecular orbital is the highest occupied molecular orbital. That gives electrons to form the bonds, and an electron can get promoted with light. And the LUMO is the lowest unoccupied, this should be unoccupied, molecular orbital, and that one is going to accept electron density. So you can see the LUMO here has no electrons in it, and the HOMO has two here, but that can get excited so that there's one unpaired and one unpaired one there. You don't have to worry about duplicating any of these molecular orbitals. I have nightmares about molecular orbitals, so I'm not going to impose that on you guys, but these do explain some of the reactivity behind the Diels-Alder reactions, so we just kind of have to look at them a little bit. We can do different reactions with conjugated dienes where we can control them with the temperature, which is one of the things that you'll be looking at in lab. So with high heat, you're going to get the thermodynamic product, which is what results in that is a more stable alkene. It's also a slower reaction because it can take its time with that extra energy to produce the more stable reaction. And with a heated reaction, you're going to get a more stable alkene. So if you look at this first reaction with the diene, you have the alkene that's going to attack the HBr, and that kicks the Br electrons off. And if you have your Br next to the carbocation, which is forming at carbon 2, that is the kinetic product that forms. And that is from cold. That one just happens right away because of proximity. The bromide ion is really close to 2, so it's just going to attack there. But if you have the warmer conditions, we can form a resonance structure where these electrons move over to between 2 and 3. So you form this resonance structure here. That carbocation moves to 4, and that makes a more stable alkene when Br attacks 4. In the kinetic product, your alkene is monosubstituted. And in this product over here, the thermodynamic one, your alkene is disubstituted, which is more stable than the monosubstituted. So with lower temperatures, you get the kinetic product that forms quickly, that gives you the less stable alkene, and that nucleophile attacks that first carbocation formed instead of going through the carbocation. So if you did the reaction with HBr, the 1,2 adduct, which is the kinetic one, when the temperature is cold, you get 71% yield at 0 degrees Celsius. There's 29% of the 1,4, which is the thermal product. But when you heat up the reaction to 40 degrees, that ratio changes from 15 to 85. So we have a way of favoring these reactions. If you want the 1,2 adduct, you make it cold. If you want the 1,4 adduct, you just warm up the reaction. Questions there? All right, let's switch gears to our reaction book page. We're going to start on the functional group transformation page, which is page 8. I zoomed in a little bit too much. Okay, so the first reaction is chapter 17. And we have the diene, the conjugated diene. And I'm going to number these 1, 2, 3, 4. If we add HX at 0 degrees, we'll get H adding to the end, because H is going to go to the carbon with more H's, and then the Br goes to where the carbocation is. This is the 1,2 addition. And here, oops, I put Br there, but X can equal Br or Cl. This should really be X here. And if you do this reaction at warmer temperatures, 40 degrees Celsius, the H goes to the end like normal. And then in the process, the alkene moves to here from the resonance structure. And then our X from the HX adds to the end. This is the 1,4 addition. If you add X2, so Br2 or Cl2, we would get the same pattern here. So at cold conditions, we'll get Brs here. Or those BRs can be X's. So put X over the arrow. And then for the warm conditions, we'll see the same thing. Questions on reactions there? All right. All right, what is the major product of this reaction? We have HBr, and the conditions are warm. So you can assume about 40 degrees. What product will we see here? All right, so warm is going to give us our thermo product. If we numbered this 1, 2, 3, 4, our H goes to the 1. There would be a carbocation here. And then this can go here via resonance. Carbocation would be here, and then the Br could attack there. So we would get B for that one. A better product, actually, which isn't one of the options here, is where Br is here and H is down here. And that would result from numbering the alkene this way. So you might get a product mixture of both of those products there. All right, questions on that one? So B would be the best answer. This would be the 1,2 product, which you would get if you did the reaction cold. And this one we would not see at all. All right, so how about this one with cold conditions? All right, so people are choosing A and C. The correct actual answer is A and C. So people, I'd say, choose A and C, but it is both of those. So it depends on where you started your numbering. So you would get products with the HBr in either of those conditions. All right, any questions on that one? All right, we've got one more here. If we add Br2, so our X2, and there's no temperature specified here, so you can assume it's going to be at room temperature. So if you don't control the temperature of the reaction, what product will we get? Product or products? All right, so the answer for this one is all of the above. The A would be the 1,2 product. B would be a 1,4 product. C is the 1,2 product in the opposite direction, so we would see all of those products there. Questions on those? All right, then we move on to pericyclic reactions, which are reactions where all of the bonds that are making and being broken are happening at the same time. So concerted means that it's happening at the same time. So one of these reactions is a cycloaddition. This one is the Diels-Alder, where you have a diene and then an alkene, which is called the dienophile, because it loves the diene. These can get together when their homos and their lumos line up the right way. These form a new sigma bond where you see the dotted lines. A new pi bond is formed right here, and then a new sigma bond is formed there. So this would be the new bonds that are formed. That is a cycloaddition. You can have an electrocyclic reaction where all of the 3 pi bonds are in the same molecule and it just switches places. And you form a new sigma bond here. Or you get a sigmatropic rearrangement where the whole molecule looks like it's flipping over. But if you had something like that there, that would make a different molecule than you had here. So all of those involve the same mechanism arrows where new sigma bonds are being formed or new pi bonds are being formed. So the Diels-Alder reaction was a Nobel Prize reaction in 1950. This forms a cyclohexene with a diene, which must be S-cis. So these alkenes are on the same side of the bond. And the dienophile needs to have an electron withdrawing group. So on this first example, there's X's here, which can be halogens. The electron withdrawing group can be a carbonyl containing compound like this aldehyde here. So these are electron withdrawing. And EWG is electron withdrawing. Group. And the endo product is typically preferred for a bicyclic compound. And high temperatures can cause retro Diels-Alder reactions to happen. So these things can go backwards. So if we look at this first reaction here, you have the diene. And then the dienophile has the 2 halogens. What's happening is one of these pi bonds goes to form a bond here. So while this is being made, this one shifts to here, these shift to here, and you're forming a new bond there. And so this is the new bond that you formed. This is the new bond, and we have a new pi bond here. And the X's are on the top side, meaning that the alkene or the dienophile approached from the bottom side to form that new bond. If you have, so that's with a Z alkene. If you have an E alkene, one of these groups will be up and then one will be down. If you're dealing with a cyclic diene, the same reaction can happen. We have dotted lines here. And then this bridgehead right here is from this one getting pushed up when that reaction or that diene approaches from the bottom side. And so we get this endo product versus the exo where these are up. So the endo has the aldehydes pointing down. And this is kind of hard to see. You got get used to drawing these, but if you were drawing this flat, you have your cyclohexene that was formed, the two aldehydes, and then you can just draw your bridgehead right there. So that is what it looks like, flat and not in this kind of 2D dimension here. All right, questions there? So if you take out your carbon-carbon bond forming sheets, we can add the Diels-Alder reaction to our books. So I start with a diene. I'm going to put an R group on there just so I have an electron donating group because that helps the reaction. And then here's my dienophile with an electron withdrawing group. You don't have to add extra reagents. We just warm it up a little bit, and you'll be doing one of these in lab as well. So I have electrons going there to form a new bond. Electrons going to form the pi bond there, and then these ones will form a new sigma bond. So there's the new bond that was formed. This is a new bond. This is a new bond. So we make cyclohexene. And then EWG is an electron withdrawing group. So this can be an aldehyde, carboxylic acid, ester, a CN. It can also be a halogen. All right, any questions on that reaction? So that's just the one that we have to add. There'll be an extra one tomorrow for 17C, but that's the general Diels-Alder reaction. All right, anybody still writing on that one? All right, so what is the major product of this reaction? All right, so we have a whole bunch of different answers here. This is Diels-Alder reaction. Hopefully you recognized that. So the arrows that we are drawing here, there's a couple of things I need to do. My diene for me is pointing the wrong way. So I'm going to redraw it like this. And my alkene or dienophile is fine. And then I draw my arrows. This is going to form a new bond here. These will go to form a new double bond. This is going to form a new bond here. All right, and that aldehyde is my electron withdrawing group. This is the new bond that I formed. So I have cyclohexene, and then I don't want to forget about the other bridgehead there. So that's the second one. So we need to have, with A, that one is pretty close, but you're missing the bridgehead. So that one's not right. And then C, that one is oriented in the wrong direction. So our answer left is B. So this is not the best drawing here. I'll try to redraw that. All right, so you have that extra bridgehead in that structure. If you were trying to draw the way that B is drawn, what you can do is kind of draw a tent like this. If you want to call that a tent, then you draw in the aldehyde group and then just put these extra bridgehead carbons back at an angle. And then you have that extra methyl group coming off of there. So that is one way to draw that one. I think when I learned it, I did it this way, which they both look similar, but whatever works for you. If it's easier for you to see them drawn flat, like we have up here, then you can certainly draw your answer flat. If it helps you to see that the bridgehead is up, then you can draw it that way as well. All right, questions there? All right, how about this one? We have cyclohexadiene plus an alkyne and carbonyl. All right, so with this one, the mechanism arrows are the same. And it's kind of oriented better than the other one. So we take one pi electron to form this new sigma bond. These will go here. This goes here to form the new sigma bond to this one. So we're not losing any carbons. We're just forming two new sigma bonds and one new pi bond. And so in A, we're missing carbons. Whoops. Because we lost that bridgehead carbon. B is actually the same as A. It's just drawn flat. This is also missing C's. So C has the extra carbons and it has the alkene here. So if we're looking at the alkyne, which you can use as a dienophile, one of those pi bond electrons were used to make that sigma bond, which is this one right here. This is a new bond here. And if it only took one, there should be a double bond left over, which this one shows here. So if you were going to draw this one flat, I'd have my pi bond left over. This bond was formed, this one's formed, there's this one, and then you have the bridgehead carbon in between there. So D is missing the double bond. All right, questions there. And you'll get an opportunity to do Diels-Alder reaction in the lab this week. If you wanted to do extra ones, as with any of the labs, you are welcome to do extra reactions. All right, so which of these we want to identify if they're conjugated, accumulated, or isolated. The first one, this is a molecule that is involved in the citric acid cycle, which is one of our biological pathways that's used to make energy. We're looking at alkenes that are conjugated, and remember that they can be conjugated with heteroatoms. So this would be one site of conjugation. And then you have another one right here, which is also conjugated. If you were going to compare it to the one carboxylic acid off to the side, because there's an sp3 here, that one would be isolated. All right, and then if we're looking at B, which is ocimene or essential oil, this one right here is conjugated. We have that single bond in between there, but if you were looking at these two, this is isolated. For C, if you were looking at this one over here, this one is isolated. And then this one right here is conjugated. That carbonyl to the carbon double bond is conjugated. All right, so this one is conjugated. And that other one was isolated. All right, what do you see for the R-carbone, which is our spearmint flavoring? What kind of alkenes do you see there? This one right here is conjugated. And if you're looking at this one all by itself and any other dienes, this is isolated. All right, questions on any of those? All right, number 2, we're looking at predicting products and proposing a mechanism. So in both of these reactions, the reaction temperature is not specified. So we have to assume it's going at room temperature. And so we're going to get a mixture of products here. And if, depending on where you start numbering, let's say I start numbering this way, you might get a mixture of products. So this will be doing a proton transfer. Our hydrogen goes to the carbon with more hydrogens. we get a carbocation. So in one version, the Cl- that was formed can just attack that one. So we'll get our 1,2 product. We can also form a resonance structure. So that our carbocation is there. And then our chlorine can add to that position. So that would be one version of products that we can get there. You could also get the products if you number them this way. So for the 1,2 product, you would see this one. And for the 1,4, you would get that product there. So these are the 1,2, 1,4. So there's a couple ones that are possible there. And the second one, our molecule is pretty much the same when we number them in either direction. The mechanism is the same. So I'll say this is 1, 2, 3, 4. Get a proton transfer. My chlorine can go there. And then we have our resonance structure that we can draw. And then we'll get the other product there. So this would be the 1,4. And then we had our 1,2 that was up here. All right, questions there? All right, so what are other products of these reactions? We have specified warm here. This is the thermo product. Cold is the kinetic product. So the warm ones should favor our 1,4. So here we're going to add H. That double bond will have shifted, and we'll get our Br adding to the bottom. So this is the 1,4 product. And for cold, we should favor the 1,2 product. All right, any questions there? All right, how many of these or which of these have conjugated pi systems? Which of these have conjugated pi systems? All right, so how many do you think have conjugated pi systems? All right, so most of you are saying 5. So conjugated, remember, is double bond, single bond, double bond. So the ones that are immediately jump out at me anyways is benzene. That one is one I remember is conjugated. So that's 1. This is 1. This one has double bond, single bond, double bond. So this is 1. This one has that same pattern here. So that is also 1. And then this one as well. So we have 1, 2, 3, 4, 5. The ones that are not, this one has 2 single bonds here and an sp3 in between. Same thing with that carbon. This one's got an sp3 in between. This one has sp3s, and that's why those ones are not conjugated. Questions there? All right, here we're looking at 2-ethyl 3-methyl 1,3-cyclohexadiene. It's treated with HBr at room temperature, which means we're probably going to get a mixture of reactions, show a mechanism of the products. So we have to start with drawing the structure. Cyclohexadiene, I have a 6-membered ring. My double bond starts at 1 and 3. 2-ethyl, 3-methyl. All right, and then we're reacting it with HBr. So I'm going to do a proton transfer first. That forms a carbocation. That first Br minus can attack to give me the 1,2 product. Have our resonance structure I can draw here. And we get the 1,4. You can also get the products if you numbered in the other direction. So for your 1, 2, you'd have the chlorine, or sorry, bromine here. And for the 1, 3, I'm sorry, 1, 4, your bromine would end up here. So you can get a nice mess of products there. Questions on that problem? All right, next one. Did I skip one? Nope. Okay. Diels-Alder reactions. So we have our diene plus our dienophile that has 2 electron withdrawing groups on there. That means this reaction will happen fairly quickly because their homos and lumos are lined up. So we're going to form a new bond here. This will form a new pi bond, new bond here. So this is our new bond, double bond there. And then we didn't really indicate here, but these are on the same side as each other because the alkenes, this was an cis alkene to begin with. And I only point that out because on the second example here, we have a trans alkene. So if I was going to draw this here, it would look like this. So you kind of want to orient things in the right way. So all I've done is just kind of turned it 90 degrees to get it in the right shape. So this electron lone pair is going to form a new bond here. These will go here. That one goes there. Oops. New bond, double bond. So if you were to draw that a little bit more cleanly, one of these would be up, other one is down. Questions on that one? All right, let's look at the next one here. Why don't you guys try this one and see what you come up with. right, what product did you get for this one? All right, so we are looking at this reaction here. I'm just gonna draw out the mechanism quick. I'm gonna turn this on the side because it's easier to see. So because we're dealing with a triple bond, we should have a double bond left over. So that will be our answers, which is C. The only time we end up with a bridgehead is if we have a cyclic diene. And we'll see a couple of examples of those, hopefully, where there's a cyclic diene. That's on the next slide. And then we'll maybe see some where there's a cyclic dienophile. All right, so any questions on this problem here of how we got our products? All right, on this one, we're going to see a bridged head because we have a cyclic diene. So this one is going to be the bridged head product here. And if you turn that product, that CN on the side, we can kind of see what our product is going to look like. This is the CN. Our double bond forms here. New bond here. And then our bridgehead is the one that gets pushed up. So you'll get that product. So that's the flat version. If you want to draw it out the other way, it would look like that. With the CNs. And then your double bond. All right, and then why don't you try C? All right, great job. So everybody chose B, which is the correct answer there. So we have that bridgehead carbon in the middle. There's no double bond left on the aldehyde side because this is a double bond to start with. And we took one of those pi electrons to make a new sigma bond. All right, this one here looks messy, right? Because there's a lot of extra junk laying around. But what we have on here is a heteroatom, which is the sulfur, and that doesn't react with anything else. These are electron donating groups, which will help the reaction. And these carboxylic acids are the electron withdrawing groups, which will also help the reaction. So nothing really is different, it just looks messier. So we would go ahead and draw the same product. One of these carboxylic acids is going to be up wedged. Other one will be dashed because our alkene was trans to start with. We have a new bond here, here, double bond, and then I don't want to forget my bridgehead. There's the S, and it pops down there. All right, so I looked ahead a couple of slides and I didn't see any of the problems where the dienophile is cyclic, but we might run into that. So let's say we have this example here. Let's make that an OME. So let's say we're doing this reaction with cyclohexenone. The reaction mechanism is exactly the same. And we're still going to get a cyclohexadiene, or sorry, cyclohexene. Just that everything else comes along with the product. So we have those two new sigma bonds and that double bond there. So that would be our product if you had a cyclic dienophile. So there's no bridged carbon in this product if your dienophile is cyclic. We only see a bridged product if your diene itself is cyclic. All right, questions there? All right, let's take a look at this one. This is the similar reaction, but now we're dealing with the alkyne, which means that we're going to have a cyclohexadiene. So if we have our alkyne is the dienophile, we'll end up with a cyclohexadiene. Or something along those lines. So our mechanism is the same. And then our double bond is still there. And I left off my bridgehead carbon. That one is right there. All right, questions there? So there's the flat version and then the, I don't want to call it 3D, it's not quite 3D, but the not flat version. All right, on the next slide, we're doing this backwards. So you have to identify reagents you would use to prepare each of these via a Diels-Alder. So this is the Diels-Alder product. So we want to find out what alkene or what diene and dienophile were used to make this product. So if you remember, the Diels-Alder product is a cyclohexene, which we have. You form 2 sigma bonds and 2 pi bonds in the process. So all we're doing is drawing the same arrows, but we're going to draw them backwards. So this is the bond that was formed before, and one of this pi bond here. So we can break the sigma bond by moving those electrons there. Move these electrons here, and then these will go here to form that alkene. So if I follow the red arrows, one of my pi bonds is here now. That was the one that broke the bond to the CO2H carbon. And then I broke the pi bond to form a new pi bond right there. And then this was right there. So that is the alkene and diene that you would need to do the Diels-Alder. All right, how about you try those arrows with B? Try it with B. So here we have a bridged carbon, which hopefully signals to you that we started with a cyclic diene. So try out the arrow pushing and see what starting materials you get. Which products might we see there? All right, let's take a look at the arrows on this one. So the new bonds are usually made are here and here and there. So I'm going to draw the arrows backwards. This one goes to there. This one goes to here. I'm also going to draw this in the flat version. It might help you guys see it better. So these go here. This goes here. That one goes there. So if I follow those arrows, I think we're about to crash again. I think the right answer there was B on that one. So I'll draw this again real quick here. So we end up with the double bonds there. And then one was on that one. So that should be the correct answer. You have cyclohexadiene plus the alkene, which has 4 nitrile groups on that one. All right, any questions I can clear up on that one? I know that one was a little bit messier. Okay, so bridgehead carbon is the result of a cyclic diene. And then we had the external dienophile here. If you have a system where you have 2 rings, like we saw in the last one I showed you that example, that is the dienophile that's going to be cyclic. So what about this one right here? What dienes will we start with on this one? Why don't you try drawing the arrows? So we have a bridged head molecule and also a cyclic molecule on the other side of that. So what do you think that one's going to look like if you draw the arrows backwards? All right, good. So most of you are on the right track here for drawing our arrows backwards. This one forms a double bond here. That one goes there. This one goes here. So remember, when we're doing a Diels-Alder, we need a diene, which has 2 double bonds plus a dienophile. So if we follow those arrows, we're going to end up with A. B is pretty close, except this double bond here is in the wrong spot. Remember, we need a diene and a dienophile. This one has 2 dienophiles. So we don't want to just cleave along there. We want to draw the arrows backwards to get the diene. If we did a Diels-Alder with C, we would just get this one here. And then if we did the Diels-Alder with D, we would get that product. That one will give us this one right here. Questions there? All right, that is the last problem that I had today. So if you have questions, you can ask them now or hang around and ask them after class. Otherwise, I will see you all tomorrow.